Okay, I'm just getting situated here. All right, so that's we started with pH and titratable acidity last time, so we'll continue. Hopefully we can finish it today. So let's get started with answering some of these questions via chat, or you can unmute yourself, whatever you're comfortable with. So if two acids have the same concentration, do they always have the same pH? Yes or no? All right. So I get all of this no, very good. Because they can have different pKa values with multiple ones. True. And yes, so that is very true. And just to clarify that, meaning that depending on their dissociation, some acids dissociate almost 100%, like strong acids. Other acids, like organic acid, they don't dissociate in water fully. They dissociate at much less percentage. So the pH is a measure of the active acidity. So measure of the hydronium ions, the H++ water gives you the hydronium ion, and that's what the pH measures. So it doesn't mean that at the same concentration you're going to get the same pH. They vary in their dissociation of their protons. What does titratable acidity affect in food? Let's see. We're getting quite a few answers here. The flavor, the sourness and flavor, yes. Other than that, maturity. Yes, very good. What about pH? Enzymatic activities. Yes, shelf life is dependent on multiple reaction. One of them is enzymatic, chemical, and microbial growth. Very good. Okay, so what is pKa? Let's see if you remember that. 50% acid, 50%. Okay, so I get, yes, pH at which 50% of the acid is dissociated. That's the actual best answer. So it's the pH at which 50% of the acid is dissociated and 50% is in the non-dissociated state. And that's when the pH equal the pKa, that means you have maximum buffering capacity, resistance to change in pH. Because you have to remember the Henderson-Hasselbalch equation, which is pH equal pKa plus log the concentration of conjugate base over the concentration of the acid or non-dissociated acid. And when they're equal, log 1 is 0. So pH equal pKa. Can an organic acid buffer at multiple pHs? How come? If yes. Yes. If they have multiple carboxyl groups, that means multiple COOH. So that's the group that can give up the proton. So if they have multiple ones, they have multiple dissociation factors, therefore they have multiple pKa's. This means they can buffer at multiple pHs. So you have, at different pHs, you might get pH equal pKa, and then you get a high buffering capacity. And at another pH that equals the second carboxyl group pKa, you get buffering at that pH, and so on. So for example, citric acid has 3 carboxyl groups. So you have 3 pKa, so it buffers at 3 different pHs. And acetic acid, for example, as one carboxyl group, so it buffers at just 1 pH. Okay, so good. This is a good refresher, so we can move on. We were at this slide, and if you remember, we talked about the ion product constant of water, which is at temperature close to room temperature at 25 degrees C. It is about 1 times 10 to the negative 14. That's the ion product constant of water. So at pH 7, you have equal concentration of hydronium ion and OH minus. So this means you have 1 times 10 to the negative 7, which is the concentration of hydronium ion, and the same concentration for hydroxide ion. So that means this is pH 7, equal concentration. And pH is basically related to the concentration of hydronium ion because it's pH. There's also pOH if we want to determine the pOH based on the concentration of OH group. But we never do that. We only relate to pH, which is related to the concentration or the active concentration of H plus in the form of hydronium ion in water. So the pH is negative log the concentration of hydronium ion. So with this in mind, let's work together on this calculation. There will be several calculations today, so pull up a piece of paper or in your notebook, do the calculations, take a picture of it, and we'll have Laura put an extra credit assignment for next Wednesday by 5 p.m. Maybe Wednesday or Friday. I think next Wednesday you have a lab report due. So we'll make it not this Friday, the following Friday. Okay. So yeah, take a moment and calculate the concentration of OH minus. And then the pH. And you can type in answer when you have it. pH 3.45 is correct. And the concentration of OH minus is 2.81 times 10 to the negative 11, and that is correct. So basically, you just want to know how to use your calculator and the log and anti-log thing. For the concentration, you just plug in the concentration of hydronium ion times X, which is the concentration of OH minus, that's what you're solving for, would be equal 1 times 10 to the negative 14. That's always the value here. That's always this concentration times this concentration equals this, regardless of what these concentrations are. You always have that final concentration, which is the ion product constant. So if you have this value, you're just solving for x. And just following your algebra, you would get 2.82 times 10 to the negative 11. And for the pH, you just apply the pH equal negative log the hydronium ion. So this is just a function of your calculator, just to get the log. I do it in a certain way. It depends on the calculator that you have, but generally it's easy if you have the anti-log, so you can get that number. If you don't know how to use it, just Google how to use the calculator that you have to get the negative log of a value. Okay. If you want to take a picture of this, you can as well. All right, moving on. So if you have a beer of a pH of 4.30, what would be the concentration of the acid? So again, you apply the same pH equal negative log, and you solve for hydronium ion concentration. So what would be that value? Yes. So it is 5 times 10 to the negative 5. Again, it's just a matter of plugging in your equation and figuring out your calculator and the use of negative log to get your value. So I do it in a step way. If you want, you can do it stepwise or not. Depends again on the type of calculator you have. But again, it's just a simple plugging of the equation to get that 5 10 to the times 10 to the negative 5. All right, so the pH meter, just a quick here. So the pH, oops, see. So the pH meter is a device that allows us to determine the active hydrogen ion, or the amount of hydrogen ions that are active, and it is related to the concentration. So the pH is directly related to the concentration of the free hydrogen ions, or hydronium ion. And the way it works, it's a potentiometer. So the way it works is basically measuring a voltage or electrical potential at a very, very small amount of current, a very small current. And the change in potential, so usually you have a reference electrode and you have an indicator electrode. So the change in potential when a current is run and when you have a sample, it is proportional to the concentration of hydronium ion. So that's all you need to know about that. And the other thing is uh, the electrodes themselves. They used to be a reference electrode and a detector indicator electrode separate from each other. But then more nowadays, a newer pH meter would have one electrode or one compartment that has both the reference and the indicator electrode together. So guideline to use the pH meter, you already, I think, used it. Not I think, for sure you've used it in lab 3 when you were preparing the buffers. And the first thing you want to do is make sure that your pH meter is calibrated. So you would calibrate the pH meter using usually two different solutions or three, but sometimes it is only 2 point calibration, and you want to make sure that the pH standards that you use are 3 pH units apart. So either pH 4 and pH 7 or pH 7 and 10. You can use the three of them if you want to do a 3 point calibration. Proper maintenance, meaning you just follow the instructions. You clean the electrode. If you are like measuring pH, the pH of a solution that's high in protein, you make sure that there is no protein residue on the outside of the electrode. So you oftentimes we immerse it in a pepsin solution where you have an enzyme that can break down the protein accumulating on the electrode. We can wipe it with alcohol if we have fatty substances. Anyway, there are instructions that come with the pH meter to make sure that it is clean between uses, and also it's not dried out from, or like the storage solution doesn't get dried out. So it has to usually be stored in KCl solution. So it's just a matter of learning how to use pH meter. It's pretty straightforward. You take care of it, you calibrate it every time you use it, and off you go with it. So moving on to titratable acidity, again, it's a measure of the concentration of the intrinsic acids in food. So, or the organic acids that are commonly found in food. So the organic acids that are commonly found in food can be many. Some of them are like citric acid, malic acid, like in apple, lactic acid in dairy type of foods, tartaric acid in grapes, and so on. So there's so many different ones. And in food manufacturing, we also can have different acids that are added, like phosphoric acid, added to some acidic beverages. Carbonic acid is actually formed, let's say if you take a soda that is carbonated, obviously. So CO2 in water forms carbonic acid. So it is a natural kind of like present due to the presence of carbon dioxide in water. So we use to determine titratable acidity, either we use an indicator or a pH meter. An indicator is basically a dye that changes color based on the pH. So at the end of the titration, because it's a titration, so you have acid, you titrate with base. So at the end point or at equilibrium, you would see a change in the indicator color. And that would be the end of your titration. The last drop will cause a change in the indicator due to a change in pH. So you can either measure a change in pH by a pH meter or have an indicator and measure and stop titration when you see a change in color that is permanent, doesn't fade. So the titratable acidity is based on the buffering capacity of the acids or the organic acids. That's why I bring back here the buffering principle that we talked about earlier in the semester, which is that the buffering principle, meaning that the solution resists change in pH. So that means if you're titrating an acid solution with an NaOH or a base solution, when you add your OH, that means OH minus coming from the base, you have your organic acid, and because it buffers, they will give up a proton and thus resist the change in pH. So, and because these organic acids are weak acid, that's why they buffer, because you have their weak acid form and then the salt, which is the conjugate base form at the same time. So that means the weak acid, when you titrate with base, is going to give you a proton. And then if you're titrating with an acid, then the salt is going to pick up, or the conjugate base is going to pick up a proton, and then therefore your pH will resist changing. We already said that all food acids are weak acids, weak organic acid, low percent of dissociation, and therefore we have buffering happening in these systems. Again, here's a reminder of your Henderson-Hasselbalch equation, which is pH equal pKa plus the log of, again, this is conjugate base concentration, which is the dissociated acid or the salt. So they all mean the same thing in this situation. And then HA means the non-dissociated form of the acid. That means the acid that has still its proton attached to it. And like I said, for pKa, when pH equal pKa, that means your concentration of conjugate base equal the concentration of acid. Here, that means this is 1 and log of 1 is 0 and pH equal pKa, you have maximum buffering capacity because you have equal concentration of conjugate base and non-dissociated acid. So in that case, if you titrate whether with acid or with base, you have a plateau of the pH. It does not change. So when we're titrating, we want to reach the end point, which is the point of equivalence. Number of equivalents of acid equal number of equivalent of base. So that means you get total acid neutralization. So you continue titrating until all of the HA give up their H. When you don't have any more HA because you're continuously titrating with OH minus with your base, when you're continuously titrating with this base, this HA is continuously giving their H, giving up their H until there's no more HA. Everything is in A minus form. At this case, the log A minus over a very, very small concentration of HA will increase the pH dramatically. So you get a rapid increase of pH is noted when we get to a point where HA is depleted or almost depleted. So you see a sudden rise or a quick rise in pH, and that if you are measuring or measuring neutralization using pH meter, you just detect a very quick increase in pH, rapid increase in pH. And that's when you know that the reaction or the titration is done. You reach the end point. So this is something that we do normally work on in the lab, which you will just work on by doing calculations next week. So we plot titration curves. So they look different for every type of acid. So I'm just putting this here out of the way for a little bit. So this is a titration curve here on the left, upper left, is typical for a very strong acid, in this case, HCl. So as you titrate with NaOH, we see just a slight increase in pH until, so we see this incline in pH until we reach all of the H pluses being neutralized, we see a sudden increase. And at the midpoint here, somewhere between 7 and 8, it is the end of the titration. Okay, however, if you have your weak acids with, like this here is acetic acid, so you have one carboxyl group. Here is citric acid, you have 3 carboxyl group, 1, 2, 3. So you have 3 pKa's, each one of them have different dissociation coefficient for the protons, for the hydrogen. So if we look at the acetic acid, which has a pKa of 4.75 for the dissociation of this hydrogen, when we're titrating to neutralize, you see that we see an increase of pH until we get to the pKa value, which is 4.75. You see some kind of flattening here a little bit around the pKa value because if you have maximum buffering capacity, so you're titrating and titrating and you barely see a change in pH. And beyond the 4.75, you start seeing gradual incline until all of your non-dissociated acids give up their hydrogen, and we see a steep increase in pH, and we usually get the midpoint here of the pH, which is somewhere between, close to 8, 8.2. And when you try to determine the amount of NaOH used, you just take that point here at this midpoint and extrapolate to determine the volume of NaOH used, which you will need in the equation later on, the equilibrium equation that you would use to determine total acidity or titratable acidity. The citric acid here, it has 3 pKa's, like I said. So each pKa is different. One is 3.06, one is 4.74, and another is 5.4. So you see kind of a ladder in this titration curve. So when you're titrating with NaOH, we see an increase, then a plateau around the 3.06, and an increase, a slight incline, and then again a plateau around the second pKa, and then an incline and a third plateau. After that, we see an incline until there is no more HA or non-dissociated acid, and we see this rapid increase in pH. You take the midpoint, extrapolate, and then you get the volume of NaOH that was needed to reach equilibrium. So let's go back to doing some calculations here to gradually get us to calculating titratable acidity. So at pH 4.7, what percentage of lactic acid is dissociated and present as this? That's the conjugate base. That means the lactic acid has lost an H group or a proton. And here you have the pKa of lactic acid at 3.86. So you have the pH, you have the pKa, and you need the concentration in percentage of conjugate base. So you either have conjugate base or non-dissociated acid. So here, meaning you need to use your Henderson-Hasselbalch equation. So go for it. Okay, so I'm starting to get something here. Yes, that is correct. All right, Jean, would you mind sharing how you got to this value? Just to mix it up a little instead of me just showing you the equation.
Yeah. So basically, I just use the equation, the pH equal pKa plus log concentration of A minus over concentration of HA. And I just plug in the number that I know, which is 4.7 equal to 3.86 plus log of HA over 1 minus 1 minus A minus. And then I just solve for it.
Yeah, that
Yeah.
is exactly how you do it. So here we go. Thank you, Jean. So yes, it's basically a matter of knowing the equation. So you just have to remember the pH equal pKa plus log of the concentration of A minus over concentration of HA, which is the non-dissociated acid versus the dissociated acid, conjugate base, or salt. All mean the same thing. And you just solve for A minus if you're looking at percentage. So you can say either 1 minus concentration of A minus, or you can say 100 minus the concentration of A minus, and you plug that in. If you put the 1, then you'll get the value in a decimal, 0.87, and the other one would be 0.13. If you want it in a percentage, you just multiply by 100 and you get that percentage. So pretty straightforward. Again, you just want to know the equation, and you also want to know how your calculator works in terms of log. All right, good. So equivalence point. Like I said, when we reach equivalence, we see a rapid increase in pH. So the last drop that we add, which is base, when all the H's are gone or utilized or given, then the last drop of OH minus or of the base is going to increase the pH rapidly. And that's when you know that the titration ended. If you're doing a pH meter or a potentiometric titration. So we just monitor when the pH increases rapidly. We know that the titration ended and we reached equilibrium. Um, so it is a good method. However, sometimes the pH response is slow. So you're titrating drop by drop and you wait for your pH to stabilize its reading. So it kind of teaches you patience, but yeah, that's a disadvantage that we have to wait for the response. Indicators are often used, and phenolphthalein indicator is clear in acid, and then it has red color in base. So the last drop, when all of the acid has been utilized or neutralized, then the last drop of your NaOH is going to turn your indicator color red and or slight pink, and you wait for it to stabilize. Sometimes it turns pink and then but after a little bit it fades, so you want to titrate until you get that stable pink color. And it is perfect because it changes color when the pH is between 8 and 9.6. So it's slightly above neutral, but that's where actually the endpoint is at. So the endpoint pH is 8.2. You would think that the endpoint pH would be 7, but it's not really. The endpoint pH is 8.2. Anybody can tell me why the endpoint pH is slightly basic? No, it's okay. I wouldn't think you would know this right away. It's because when you have these organic acid and then the conjugate base is slightly basic. So the salt is slightly basic. When all of your HA is being dissociated and you get A minus, this is slightly above 7. So that's why the endpoint is really not 7, it's 8.2. So, and it's perfect for organic acids because they do none of them buffer at that pH. So, which is good. You don't want an acid that buffers at that pH. Otherwise, you don't see the color, and then the pH doesn't change. So, so that's good. So this works out for phenolphthalein indicator, but sometimes you do have a beverage that has phosphoric acid, for example, added to reduce the pH of that beverage, such protein acidic beverages. Or you have this carbonic acid, which is formed in sodas. So in 7 Up, which is the beverage that you potentially would determine titratable acidity in the lab, it has CO2 and water, you have carbonic acid. They both buffer around this pH. So it's going to be really tricky if you have carbonic acid in there and then you're titrating and the color fades and you keep titrating and the color fades. But it really is fading, although you reach neutralization, but then the color keeps fading, then you overshoot your titration, you overestimate titratable acidity. So that when we have carbonic acids, such as in soda, we do have to boil off the CO2. So that's something we do in the lab. We try titrating without boiling off the CO2, and then we titrate after boiling the CO2. And you will notice that titratable acidity would be less after you boil off the CO2. Then it gives you the actual acidity of the beverage, irrespective of the CO2 present in there or the carbonic acid that formed in there. So that's one thing we will be doing in the lab. But let's say you have phosphoric acid and you want to account titratable acidity of the organic acid in your sample and potential presence of phosphoric acid or carbonic acid. You want to get that uh, titratable acidity to include these two acids. In this case, we don't use an indicator because we know that the color is not going to be stable and we might overshoot. In this case, we just use a pH meter and we just monitor when we have a sharp increase in pH. We know that that's where we reach the end of the titration. Same when we have a beverage or a food sample that has a color, like deep color. Like I say, we're doing grape juice or something like that that has a deep color. Indicators don't work in this case, obviously. Then we also use a pH meter, and that's when we have to be patient and allow it to stabilize when we're taking the reading. So we titrate very slowly and try to make sure that the pH meter has time to stabilize the reading. So what potentially you would have been doing in the lab, but you'll watch a video about it, is standardizing NaOH solution. It's important to standardize the NaOH solution because you're going to use this normality to calculate titratable acidity. So you want an accurate normality. Sometimes you weigh your NaOH and bring it up to volume. You think that you have 0.1 normal, but it might not be exactly 0.1 normal. So you really want to calculate that normality accurately. Another reason for standardization is not just to make sure that you've accurately produced this 0.1 normal, but also NaOH is very reactive with CO2 from the environment. So if you have CO2 and it got dissolved in your solution, your NaOH will react with CO2 and you get sodium carbonate, and it would precipitate. So this is a salt that will precipitate, and then you will get a reduction in the concentration of NaOH. So that is why we need to standardize, and we need to prepare our solution using CO2-free water. The way we produce CO2-free water is basically we boil this water so that any dissolved CO2 get boiled off. And we store this water in a flask or a container where we can connect it to a tube. At the end of that tube, an aspirate trap is attached. So this aspirate trap has inside of it has a silica covered with NaOH. So you have this coated silica that is coated with NaOH. So any CO2 in the air over your water will be trapped. That means CO2 will be trapped with the NaOH on that silica. So it won't make it to the water. So prevent the water from having any more dissolved CO2 in it. So that's what we would use in the lab when we're preparing these NaOH standard solution. And if we need water to add to our sample in order to determine the titratable acidity, we use CO2-free water. Okay, now how do we standardize this NaOH solution? We standardize it against a standard acid. So we have potassium hydrogen phthalate or potassium acid phthalate is in powder form, and we weigh a known amount, a specific amount of it. We dissolve it in a specific amount of water, and then we titrate this acid with the NaOH solution. So we'll go over that in lab next week. You will watch the video and we'll do the calculations together where we use the known amount of potassium hydrogen phthalate to calculate the actual normality of NaOH, which you will use in calculating titratable acidity. So here's the calculations for titratable acidity. Again, this is the same equation that you've seen since we went over proteins when we calculated nitrogen. So the weight equals normality and multiplied by the volume of the titrant. In this case, you normally multiply by molecular weight, but here it's equivalent weight. I'll explain that in a second. Divided by the weight of the sample, you correct, since volume is in milliliter, you divide by 1,000 to convert to liter, and then you multiply by 100 because it's a percentage. So this equation is the same equations we've used. You've used it earlier, we derived it earlier. Now the only difference is here you use equivalent weight instead of molecular weight. Now pay close attention. Why do we use equivalent weight here? Because what gets transferred in the equation is the hydrogens, right? So it's not one hydrogen you have here. You have an acid that could potentially have multiple hydrogens. So you could have a citric acid, for example, has 3 hydrogens. So it has, the number of equivalents is 3, not 1. And malic acid, which is the acid in apple, which we will potentially be titrating in the lab, has 2 carboxyl groups. So the number of equivalents is 2. So when we're doing equivalence reaction, you have to take into account the number of equivalents. In the past, the number of equivalents was always 1, so we used molecular weight. But because now we're working with acids that might have more than 1 number of equivalent, you have to account for that in the equation. So molecular weight divided by number of equivalents equal equivalent weight. So if the acid is, let's say, acetic acid, so it has 1 number of equivalent is 1, so we can put the molecular weight directly of acetic acid here. If it is citric acid, we have to divide the molecular weight by 3. If it is malic acid, we have to divide by 2 the molecular weight. So now you would say, would I give you this in an exam? Yes, I would tell you. I would tell you, for example, it has two carboxyl groups. Or I would give you two pKa values so you know that it has two carboxyl groups. So I will give you a hint in a way that you would know that the molecular weight needs to be divided by 2 or by 3, depending on the acid I give you. I don't expect you to remember that citric acid is 3 and malic acid is 2 and acetic acid is 1. No, I'll give you a hint about that. But what you need to remember in this case, because of the acids and multiple number of equivalent, it's not just simply the molecular weight of the acid in this case. Okay, everything else about this equation is the same as we had talked about derived in the past. Okay, so let's solve this together. So here's your hint, citric acid. I drew it for you. Instead of telling you how many pKa's, I just drew the structure. So you have 3 carboxyl groups here. So go ahead, take a moment. Okay, let's see. Yes, it is 0.6% on average. It's a percentage, not per liter, because you multiply by 100. So it's basically weight by volume. So you would get a grams per 100 ml. So here it is. So you have your normality of NaOH, which is zero point zero 0.08 normal, same as 0.08 molar. So it's 0.08 moles per liter. And then the titration is 17, that's the volume, 17.5 ml. Because it's in milliliter, we need to convert to liter, you divide by 1,000. And then here you have 192 molecular weight, so you divide by 3 because you have 3 carboxyl groups, you get the equivalent weight of 64 grams per mole. And then milliliters of sample, that's 15 milliliters times 100 to give you 0.6%, which is in this case grams per 100 ml. Okay, so that's what it is. So I think this is the last calculation we have. So make sure you take a picture of your calculations, and Laura will have that extra credit assignment. There's also another extra credit assignment that I put on Canvas for pH and titratable acidity, and it's for +5. I will check, maybe we can make it due Monday the 16th. Yeah, I think that would be it. No, not Monday the 16th, Monday the 14th. Okay. So Laura is here, so she's probably taking note of that. Okay, so this is a table here really quick. I know we reached the end, but this is going to take a minute just to finish this lecture. So it's just an FYI table to show you the typical percentage of acid. So again, to give you an idea that really percent acidity won't be high. It rarely is above 100. Very small, lemons are very sour, so obviously they're high in acidity compared to the others, but everything else is really potentially 1 or less percent. Lastly, here, titratable acidity, again, it's you measure it using the predominant acid. Sometimes you can have multiple acids, but you use the molecular weight of the predominant acid in that sample instead of multiple. And often we use Brix to acid ratio to predict flavor because sugar impact the sourness. So Brix is a measurement of the soluble sugars, and then that ratio is a better predictor of acid flavor. And sometimes we need to know the volatile acidity. So let's say if we have wine, we don't want acetic acid to be in wine. So a high amount of acetic acid is a lower quality for wine. So acetic acid is volatile. So you can measure acidity of the wine before you boil off acetic acid and after you boil off acetic acid. Then you can get the difference to determine acetic acid concentration. So with that, we'll have a video on the lab, and we'll go through that video what you're going to supposedly be doing, and then the calculations and the questions we'll solve like we did this week, next week virtually in a Zoom meeting. Okay, with that, this ends this lecture, and then Friday we have a special guest. Make sure you're there. I'll send a note about that. We'll give you a guest lecture. All right. See you later, guys. See you on Friday.